You might be thinking it seems like we've said everything that we can say about the law of sines yesterday. It seems easy, it seems fun, and it is. But if you're given the case like the warm-up, then it is very easy and pretty straightforward, like Ashley has demonstrated so well. If you're given two angles and a side. So we'll see why it could become more complicated in a minute. But let's stop and just look at the road map for a second, see where we are. Look at the map and see where it says you are here, right? So this is the case that you just saw in the warm-up. Any of these cases, you might say, right, is good. Just use the law of sines and find the angle side pair, set up your ratio, and go. So notice that I'm highlighting any of these cases. And the movement of the letters, what does that mean? Well, it means that even if I give you two angles and a side that's not between them, that's fine. If I give you two angles and the side that's between them, that would also be fine. The point is you can easily get the third angle if you want. Right? So any of those situations we've seen from your homework last night is not too bad. All right, well, what other information can we give you when it comes to solving a triangle? Well, if you'll recall from your geometry class, certainly two angles and a side determines uniquely any triangle. But also, two sides and one angle, if the angle is included, determines a triangle. And three sides determines a triangle uniquely, right? So definitely I should theoretically be able to give you this information. So for example, here's SAS. If I happen to give you these three pieces of information, theoretically that defines a unique triangle, and therefore you should be able to somehow come up with the other three components. But why is it a little bit problematic at this stage in your life? Or I guess I could put a finer point on it. Why is the law of sines not super helpful here?
Because none of the given measurement corresponds to the opposite measurement of what we need to.
Yeah, we have an angle and a side, but we don't have an angle-side opposite pair, which is a little bit of a problem for the law of sines. It's one that we'll be able to do, but not with the law of sines. And side clearly has a problem for the law of sines, right? Clearly that's a nice triangle. We should be able to solve it, but we definitely don't have an angle-side pair there. Both of these can be conquered using something called the law of cosines, which maybe you've been exposed to before, but we will not be talking about that today. So we'll come back to this. We've done this. We'll come back to this, I promise. We did this already.
That's a law of sines.
Yeah, we did that yesterday. We'll cover the law of cosines soon. And this is what we're going to do today, is this case here. So here I'm giving you, instead, notice the subtle difference here. I'm giving you two sides and the non-included angle, that is the angle that's not between the two, but one of the other two angles. So the picture might go like this. In yellow, say, I'm giving you these two sides and that angle. So, right. Now, it seems like it might be good in terms of the law of sines. Why? You see that we're maybe set up for the law of sines here? We do have an angle side opposite pair. So this is looking good. Now there is one thing that's maybe haunting some of you because of your experiences with geometry. There might be a footnote on this. Yeah. Unless it's in the bottom.
This one could either be this way or this way.
Yeah, I mean, I guess the thing you're thinking, Stephanie, you want to say your thoughts there? You have to use inverse sine. Yeah, you will have to use inverse sine. That's true. But yeah, talk to me. I mean, these are all things that I remember very, very clearly from my geometry class. That's right. But this is troubling for some reason, perhaps. So some of you feel it, don't you? That perhaps SSA doesn't produce a unique triangle. We'll see. And the point is, we'll flesh out. We're going to spend 15 minutes here talking about why this is a tricky situation. You'll recall from geometry is not certainly a method for proving two triangles congruent. Is that a thing you remember? Okay, so there does seem to be trouble afoot, but it's not insurmountable trouble. We're going to go there though today, because it does seem like certainly if I gave you those criteria, there's not too many options for how this triangle could look. Maybe I don't know, but it doesn't give necessarily a unique triangle. Okay. So I think we'll start by was going to say let's go to the applet, but we'll save the applet for a minute here. All right, so just so we're all on the same page here, the triangle that we're going to look at today, let's label it with these labels and orient exactly in this way. A, B, C, and sides in their usual customary positions. Okay? And let's just be clear, the things given, I'm going to kind of mimic the picture at the bottom of the last slide. The things that are given, will be this angle, this side, and this side. Angle A, and side B. So that'll be the situation we're in, and we'll try to see why this might be complicated. One thing that will perhaps, I don't know, maybe I don't want to give it away yet. Let's go to the applet. I kind of want to show you how this might look on here. All right, so here I've got a triangle set up here, and you can here are the three givens. Do you see them? Here's angle A. It allows you to set angle A to whatever you please. It allows you to set side B to whatever you please, and it lets you set side A to whatever you please. Side C, right now I have kind of like as infinitely long. I'm not sure where it is until you give me those other constraints, right? So you understand that these are the three givens. Yes?
Yes.
Good. All right, so now let's think about the conditions under which this triangle might exist. Do you remember constructions from geometry? We're going to think a lot about constructions today. Yeah. Imagine that I gave you these three things. What would you actually do if I actually handed you, there are a couple things you remember doing in geometry, some of the earlier construction. If I give you a segment of length B, another segment of length A, and an angle of size A, two of the things that were kind of basic ideas in constructions was your ability to copy an angle and copy a segment. Do you remember how to do those things? You could go back and review, but just know that one can do that. I can move a segment. You have a segment, I can, using a compass and straight edge, I can copy it to my sheet of paper without a ruler, with a straight edge and a compass. And same with angle. If you have an angle, I can copy it onto my piece of paper using a straight edge and a compass. You can think through how you do that again if you like, but just take our word for it. So here's side C. I don't know how long it is. I just have no idea. I'm just going to draw an infinite line. What would I do? Well, I'd take angle A, and I'd copy it to here. And then I'd construct side B of this known length, like that. And then what would I do to get A in here? Notice I don't know what angle to put it at here, so I can't like copy an angle in here. What would you have to do?
Would you take the compass, put it on the end of point B, and then swing it to the length of A until it reaches
Yeah, I'd set my compass open to the length A, and then I'd swing it like that, right? And then where it meets, there I'd put A, right? This is rudimentary here. I don't actually have a compass, but you can imagine the construction, yes? So that's what we're doing here. In fact, I have a circle here shown. You know, if I swept this circle, then boom, it would hit this side right here, right? Okay, now when do you see any trouble afoot? Can you imagine in this particular case right here, let's think about this particular case where A is an angle like 120. Where would we maybe have trouble afoot in this particular picture as I slide A back and forth? Everything looks fine, unless what? What do you see, Yvonne?
If angle A was really, really small.
Well, let's keep angle A at 120 for now. What about the sides A and B? Is this always going to be okay if angle A is, maybe we're always okay in this case. I don't know. Yeah.
Like 0.01.
If what bottom one? Which one?
Like the one that's like undefined.
Sorry, no, it's hard to see on here. This is side B.
You mean side C?
Well, side C is not determined.
I said, but then you see like in a case that one.
Yeah. How would you like, I'm just saying, is this situation going to break if I move these sliders in any particular way, Samantha? Yeah, if A gets too small, and by too small, what do you mean? Too short? What do you mean?
Shorter than B.
Shorter than B, right? If it's shorter than B, we have a problem, don't we? You're like, can't reach, right? That would be a problem. Then no triangle can be formed there. All right, so that's a thing to look out for. As long as A is bigger than B, we're okay. All right, let's now think about the situation where we have an acute angle. And now I'm ready to maybe hear from Ivana.
So if the angle A is an acute angle, and then you make, sorry, the angle that you just did, the one at the top right, is that A? Side A?
Angle A, side A,
Yeah.
side B.
So on side A, and then side A was just slightly longer than side B. When you swing it, it would actually intersect C at 2 points. You would know.
Okay, let's see if we can get that to happen here.
So there would be 2 possibilities. And then you shrink side A down.
Yeah, so here's the circle, and she's saying, and actually the picture I drew is that happening over there, isn't it? She's saying that there's a point at which it's possible that you could get 2 different triangles. You see, like that would be, when you're doing the construction, you'd be like, okay, did the construction, but which of these intersections are you talking about? And in the earlier cases, it was unambiguous. But in this particular case, it is, this is the name of the lesson, this is the ambiguous case, right? It's like, how can you decide where you're going to put it? And the answer is both. If you put it in either place, it would satisfy the requirements given in the problem, wouldn't it? You would have the 2 sides and and the angle in the places needed. Now there's a little more to it too, maybe. What if, so what is the requirement that happens? Let's like see if we can nail that down. When will that happen? Why didn't it happen? Let's start with that. Why didn't it happen here? Because side A is what? It's longer than B. So it didn't happen here. If side A is longer than B, we're in a good position, but we don't have 2 triangles. We only have 1 triangle if A happens to be a bigger number than B. What about, okay, so do we ever run into trouble, with A being too short at all? That is this side being too short? What if I slide this back here? Is it possible for it to be too short? Like, you want it to be shorter than B in order to get 2 triangles. But it could be too short, maybe. What's the minimum requirement for the length of A? Yeah. I think it can be shorter than B, can't it? And still reach?
Yeah. When A is acute.
When A is acute. So A is acute.
It can be shorter, but when A is
Yeah. So how short can it be, I guess, is what I want to say. I want to know. How short can it be? What's the minimum A could be? I don't know. Here, let's.
Like a shorter than B.
That's too short, right? What would you like it? What's the requirement? When will this finally work? It doesn't work here. Oh, you mean like this distance here? Okay, yeah, exactly. This distance, this perpendicular that I've just dropped, represents the shortest distance that A can be. Right? So as soon as it hits that, then we do finally get triangles, right? Good. What if A was exactly equal to the height? Then it would be a right triangle, and that would be okay too. That would be fine. All right. Now, I just wanted to like say all that before we launch into this discussion fully here, right? Because I just want you to know that all of what we're about to say is driven by the picture. Right? So the height. Why is the height B sine A? If we want to know what the height is, why do we know that it's B sine A? Explaining from the picture. We did this little piece yesterday, maybe. Yeah. A lot of what? Law of cosines. Maybe it's just. Okay. I think the law of sines is a little heavy machinery here. Whereas maybe there's a quicker explanation. What would you say, Julia? So the sine of this angle is this over B? Or so H over B is sine A. Yeah, so I think you could just like look at the right triangle and use the definition of sine to be like, oh yeah, the sine of this angle will be H divided by B. Yeah. Good. So the height is something we can get if we need to know it. And then let's, again, so we're going to move forward with this picture in our mind with these letters, but then later we will change the letters. Okay, so let's just zip through these real quick. If A is obtuse, I'm just summarizing what we've just said. Okay, if A happens to be obtuse and A is greater than B, what happens? That is the opposite side we're about to put in is bigger than B. Are we good? We're good. And as we swing there, we get one triangle, right? What if A is less than B? What do we say? Yeah, we swing here. It's like a T-Rex, right? It's like, its arm's too short to be useful. We don't get a triangle at all. Okay? We're done talking about the obtuse case, right? These are the only two things that can happen. What about if A is acute? Well, there we had a lot of complicated things to say, didn't we? If A is less than the height, notice how the H value comes into play now. If A happens to be less than the height, then what happens? That is, the side I'm going to put in is less than the H value, the minimum distance. Then we get no, we're in the T-Rex situation again. Right? It's like desperately swinging, trying to reach, and it can't. No triangle if A doesn't meet the minimum height requirement. What if A is equal to H, we said? We finally do reach. We just barely reach. A does fit right in there, perfect. And we get a triangle. It's only one triangle, and moreover, it's a right triangle. So that's not a problem. What's the next case going to be called? If A is greater than H, but we want to be careful. Greater than H, but still, we still want it to be maybe in between. Remember, we get this two triangle case when A is greater than the height. It's still less than B, right? So the next case is, what happens if A is in between the height and side B? So that's this one here, right? If that's the case, if it's a little bit bigger than the height, then we swing and we hit twice here and here. So there's like an option for A, and there's the option for A too. This is what we saw in the applet. And we get two triangles formed. There's one, and there's the other. And we're not sure which someone is talking about if they gave us those three pieces of information. We're not sure. Are they talking about this one or this one? Both of them have the prerequisite pieces of information in them. And this is the case called the ambiguous case, right? All the other situations, it's very clearly either no triangle or one triangle. And then there's one last case which we looked at, and that's if A is greater than B in the acute angle situation. Or you look at the applet. And in that case, we get unambiguously one triangle, right? We swing and it only hits once, and we only get one triangle form. So that's my summary of what we saw in the applet. Hopefully that captures what we've just done. What I don't need you to do, I don't think, and I don't recommend this, is to be like, okay, when you come up against a situation, analyze it in the following way. Okay, I need to have my flow chart out. This is case 2, part C. Okay, right? You don't. I would just go think about how we thought through it with the applet. I mean, really, we were very visually driven, weren't we? We tried to draw a picture and said to ourselves, does this make sense? And the answer was sometimes like yes and sometimes no. So, yeah, don't get too caught up in like the cases and the flow chart and all that. Just kind of draw the picture and see what makes sense. Okay, so let's work through a couple of these. We're not going to actually solve these. We're just going to say how many triangles there are. So I would actually sketch a little picture. Now notice, pretty quickly here, we have letters that don't correspond to the letters on the previous slides. Uh-oh, can you handle it? Just know that you're always going to get an angle though. In these, all of these are an angle, and two sides. So whatever, just you can still, without loss of generality, put it in the same positions that we had earlier. Right? You can still put the angle on the left, put the unknown side that wasn't listed along the bottom. Maybe this is okay. So let's do that for this first one. Let's start drawing a picture of this here. So there's angle A. I don't know how long this side C is going to be. Here's side B. I'm going to put that in. It's 8 units long. And now I'm going to swing side A, which is opposite the angle A. Is it going to work? Which situation? Again, we don't need to know which case this is. But yeah, 12 is going to fit just great there, right? How many triangles are there? Unambiguously, one triangle. There's definitely one triangle this person is talking about. And we can solve for the rest of the components of it, no problem. What about this one here? We got an acute angle. We might be in dangerous territory here. So here's angle D. It's acute. And side E we're going to put here. Again, we don't know how long this side is. Side E is 41. And now we do have a question in our mind. 26 is shorter than 41, so it's not obvious yet. We do need to calculate the height. So let's do that quickly. In this case, what's the height going to be? Well, it's always going to be this side length, 41, times the sine of this angle. So don't get caught up with the letters. I think earlier we said it's B sine A. Well, it's this side times the sine of this angle, whatever the letters are, right? So what is, someone maybe can calculate this on their calculator. What is 41 sine 49 degrees? Approximately what? 30.9. So what do you think here? Is it going to work? 26 is the length of the side we need to put in. Does it meet the minimum required distance? No. That's greater than 26. So there's no triangle here. We're back to an obtuse angle here. Let's draw the picture. So there's 115 degrees. This side here is 15. Are we gonna, how's this gonna go down? Actually, we don't know how long that is. Is 6 gonna work here? I mean, we're gonna be in this situation where like swinging and we can't reach. It would have to be at least 15 units long to reach, right? That's a problem. So that's another 0 triangle situation. Down here, we've got 30 degrees, angle Q. Okay, we don't know how long this side is. 16 goes here. 8 is going to go in here. We better check the height again, because it's not sure again. Well, the height is going to be, what, 16 sine 30, and we don't even need a calculator to say that that's exactly 8, right? 16 times sine 30, that's 1/2, is 8. So what situation are we in? We're going to put it, is it going to work? Yes. And it's going to be, in fact, we're talking about, maybe you didn't see it at first, but we're talking about a right triangle. Now we know. Down here, we've got 23 degrees for angle M. So this side here, let's make sure we get it right, is 3. This is N. And is N gonna, is M equals 3 if the other side is 3? Is that gonna be okay? Is that gonna fit in here? Yeah, I think that'll work as a triangle. Can we swing it back? What happens if we try to swing it back the other way? Does it hit over here? I mean, maybe you'd say it does, but we'd get like another triangle that's like collapsed on itself, right? So it's not really another triangle. So I would just say there's only exactly one triangle in that situation. You see how I'm just drawing pictures? At no time did I say, oh, well that is case 2 part D. You know, that is what that is though. Okay, down here we've got angle S. It's cute. Side S is going to be 100. The side here is 150. So will 100 fit? What's H? 150 times sine 10 degrees is, what'd you say, 20? All right, 26. All right, I think maybe we already knew that it would work before we started. But yeah, 100 will work, and it'll be able to be put in either one of these places, here or here. Right? We'll get 2 different triangle options for us here. Okay. Well, now we need to actually solve one of these for real. We'll solve it all the way out. Okay. But I hope you see just the general reasoning when you come to a problem like this, how the thoughts we had earlier about the picture that were very general apply in these situations when we actually put numbers to it. Okay, so here's my next problem, and I just to make it the most interesting one possible, you can guess which situation I'm putting us in. Let's take a look here. All right, so we've got angle B. Notice I've changed the names again. So this is angle B, and it's 35 degrees. Side C, we'll say is this one here, 11. Side A is the unknown one. You can extend this forever if you like. And we're wondering if 8 will fit in there. So we need to consider what the height is. Well, 11 sine 35 is approximately, I'm not the exact. What do you say? 6.3. What do you think, friends? Is this going to work? So 6.3 is that height, and the segment that I'd like to put in here is 8 units long. So I think it will fit, it will reach, and furthermore, since it's less than 11, we do have the most interesting of the cases, the two-triangle case, the ambiguous case. So we'll draw in here the first version of this triangle. 8. I'm going to call this C1, and this angle up here, A1, and this side, little a1. But we know there's another triangle too, and we're going to solve both of them when asked to do it. To do this kind of a problem, we're going to be asking you to solve both triangles. In this triangle, we have the exact same stuff happening, 11, 8, but it looks like that maybe instead. So this is, we'll call this A2, C2, and A2, how about? Right, so we're going to solve both triangles. That is, in the end, I need you to give me the value of C1, big A1, little a1, and big C2, big A2, and little a2. 6 answers when we're done, okay? So let's start doing it. Here we get sine of 35 over 8. That's the known ratio that we love. We're going to use the law of sines here. Equals the sine of, what am I going to go for? Yeah, I need to use the 11 and the unknown C1. So what's C1 going to be? Well, it's going to be the inverse sine of 11 sine 35 over 8, which is, make sure you store values all along the way. In a second, you're going to have the first thing we need. Once you get C1, are you kind of home free on this triangle? Because then you can get A1 pretty quickly, can't you? By subtracting from 180 the other two angles that you now know. And from that, then, can you finally get A1? So that would be the order that you'll get those in. And now before you go, I need to say one more quick thing. How do you get C2? I'll give you a hint. When you did the inverse sine of this on your calculator, it gave you an acute angle. The inverse sine always does. What's true about these two angles, C1 and C2? I guess you'll have to think about it. But they're supplementary. So you can take C1 and get C2 and then do the same work. More to minus. All right, you'll have one or two of these maybe like that in your homework, but most of it you'll be okay with. Law of sines, more tonight. More law of sines. Yeah. Back. Homework 6 tonight, but I'm not going to sign homework 7 tonight.